Hello everyone. Today I will give the presentation titled Neural Packet Routing. My name is Shihan Xiao. I'm from the Huawei company, Beijing, China, the Network Technology Lab. Let's begin with the motivation part. Today's distributed routing protocols are highly reliable and also provide basic connectivity guarantee. However, it focuses only on the shortest path routing, and it is also well known difficult to be extended to solve different optimization goals. It also takes a large human and time cost on protocol design and configuration parameter tuning. For future network, we will expect more flexible optimization goals. For example, the 5G application may desire noise end-to-end delay, and moreover, we will expect a highly automated network with less and less human costs. So the key question is, can we achieve the flexible and also automated optimal product design at the same time? With the recent progress, deep learning can be seen as one potential way to do this. For example, in 2018, the Google DeepMind team shows the deep learning method can achieve higher win rate than human professional players in a popular multi-agent game. Consider today's high-speed routers and switches. Using deep learning in routing seems quite difficult if the neural network inference is slow. The promising thing is that recent research also shows the feasibility to implement line-rate neural network inference in the data plane of network routers or switches. So deep learning is a good start. Here's a simple learning-based routing framework. The key idea is just to train a neural network at each network device to directly compute the forwarding port for each packet. But there comes a key question about the learning safety. As we all know, the neural network training has some unavoidable errors. So what will happen if the neural network make mistakes? To verify that, we test a simple example to supervise the learning of shortest path routing. As we find in our simulations, despite we got a high training accuracy, the neural network inference errors can raise non-standing routing loops, and such behavior can be really dangerous and unacceptable for real production network. The inference error in deep learning is unavoidable. So can we still achieve reliability guarantee while keeping the advantages of deep learning? Here we present our solution called the Neutral Guided Routing, the NGR. The NGR design includes three important components. First, it proposes a reliable distributed routing framework, and then we show how to combine the deep learning into the framework. And last, we show how to handle the topology changes. For the first part about the reliable distributed routing framework, we first define a routing path is reliable if it reaches the destination node without any persistent loops or black holes. There are three key desired properties of the routing framework. First, it should be controllable. That means it has some parameters to directly control the routing path for each packet. Second, it should have the optimality capacity. That means any reliable routing path can be implemented by setting proper parameters. Third, it should be error tolerant and also has the reliability guarantee. That means it can always generate a reliable routing path no matter what errors happen in setting the parameters. However, it is quite challenging to find such a routing framework. For the previous solution that we introduced about the direct port computing using the neural network, the solution is controllable and has also the optimality capacity. However, it has the neural network errors will need to routing loops in real examples, so it is not error tolerant and it cannot provide the reliability guarantee. Another solution to achieve the reliability guarantee is to restrict our next hop selection to use only the neighboring nodes that are closer to the destination. This constraint, we call it the triangle constraint routing. And we show that in some simple examples, the optimal solution of the triangle constraint routing cannot achieve the global optimal routing. And it shows that there's a optimality gap between the triangle constraint routing and optimal routing. So it does not achieve the optimality capacity. So here comes the key question. Can we find a framework that satisfies all the desired properties? The answer is yes. NGR proposed a new routing framework called SARR following the link reversal theory. The key idea is that we can assign a value to each node in the graph, and then the link directions can be defined from pointing high value node to the low value node. We can then add updated node value into the packet head to implement the link reversal operation. Here's a workflow example. A packet with destination D arrives at node A. Here we have two forwarding rules. The first forwarding rule is that the next hop node can only be selected from lower value neighboring nodes. And when there are multiple choices, we select the one with the lowest node value. As the left figure example shows, the next hop node of node A is node C. When the packet is forwarded from node A to node C, we can see that the first forwarding rule does not apply here. So we use the second forwarding rule. If the current node is a sync node, that means that the current node has no out links. We will perform the link reversal operation. The link reversal operation is realized by changing the current node value to a new node value. Actually, we simply set the new value as the maximum of the neighboring nodes plus 1, so that the new value is larger than all the neighboring nodes' value. We add this new updated node value into the packet head, so that the next hop node will extract the packet head to get the newest node value. Next, we just repeat using the previous rules and until the packet can reach the destination. Actually, the link reversal theory guaranteed that the packet will reach the destination with finite steps. The second part is how to combine the deep learning into the routing framework. The key idea is that the routing path is fully controlled by the node values in this framework. So we can do in NGR that it trains a neural network at each node to compute the node values, so that the neural network can learn to optimize the routing path directly. The above framework is first controllable because it can control the final routing path fully based on the node values. It is also error tolerant with reliability guarantee because the link reversal theory guaranteed the packet will finally following a reliable routing path to reach the destination, no matter what errors are happening in the neural network computation. But what about its optimality capacity? To achieve the optimality capacity of the compiled deep learning framework, we still need another fine-grained patch. Actually, what we do in NGI is to assign two separate values to each node. And we turn the value as the prime value and the second value. And the prime value is used in the first part of the rule 1. The next hop node can only be selected from the lower prime value. And we use the second value in the second part of the rule 1. When there are multiple choice, we select the one with the lowest second value. We prove that the above framework can achieve the reliability guarantee while keeping the optimality capacity of deep learning. For the next part, we show how to handle topology changes using neural network. NGR used the graph neural network, the GNN, to handle topology changes. So when the topology changes, in the first step, each node will inform its local hidden vector to the neighboring nodes. The second step, each node will aggregate the hidden vectors received from the neighboring nodes to update its local hidden vector. And step 3 is just repeat the above two steps until the local hidden vector does not change, or it reaches a predefined number of steps. In the above way, the new topology information is finally embedded into the node feature vector. By putting all the pieces together, we finally get the entire overview of the NGR architecture. First, the GM module is responsible for learning the topology information and embed the newest topology information into the local feature vector. And forwarding neural network will input this local feature vector and also the packet destination and to compute the node values. The node values form the value vector, and the SARR framework will finally select the foreign port based on the value vector. In the evaluation part, we use the topology from the Internet Zoo topologies, and we set the NGR parameter as the forwarding neural network is implemented as a three-layer neural fully connected network, and the GNN module is used the GRU network and with output feature vector of DN200. And the compared solution includes the non-learning based solutions such as the shortest path routing, triangle constraints based routing, and also the learning based solution, the GQNN. And we evaluate two tasks, the node balancing task and the shortest path routing task. In the node balancing task, we show that NGR shows near optimal performance in different traffic demand metrics. In the shortest path routing task, we simulate the routing reliability of different solutions when link fails. We can see that the compared SPF and GQNN solutions can generate more black holes and routing loops when more link failures happen. And our solution NGR does not generate any loops or black holes in all the cases, at the cost of a slightly longer routing path. We also evaluate the packet head overheads and the path length of the NGR when link fails. And we see that the NGR achieves a small path length expansion ratio, which is below 6% under all cases. And the link ratio overhead in the packet head in NGR keeps small and increases quite slowly with more link failures. To summarize, NGR is a reliable deep learning-based distributed routing solution. It is reliable because it provides the connectivity guarantee based on the link reversal theory. It is flexible because it uses deep learning to support flexible, customized optimization goals. It is optimal because it can attain the optimality capacity with respect to the given optimization goal. For the future work, we will consider to use reinforcement learning to learn more complex optimization objectives, and we will consider scalability and generalization for larger scale network topologies, and also we will consider the line-rate neural network inference design in the network devices. This is the reference of our presentation. That's all. Thank you for listening.